If you're new here, welcome. The BoreCore archive is a collection of slow, methodical recordings of technical processes and perfectly boring routines designed to help you relax and fall asleep. New procedures are added regularly, so don't forget to like and subscribe. Time to relax, close your eyes, and take it on down to Sleepy Town. This is archive recording MED-201.
Welcome. You work in the sterile processing department. It is possible that no one at this hospital knows exactly where the sterile processing department is. This is not a complaint. It is an observation about hospital geography and the tendency of essential infrastructure to be located in basements. You are, in all probability, in a basement. The sterile processing department is called several things. It is called the SPD. It is called Central Sterile Supply, or CSS. It is called Central Service, or CS. Some facilities call it the Sterile Processing and Distribution Department, or SPSD. Whatever it is called at your facility, it is the department responsible for ensuring that every reusable surgical instrument used in every operating room in this hospital is cleaned, inspected, assembled, packaged, sterilized, and delivered in a condition that will not harm the patient it is used on. This is your job. It has a great deal of responsibility. It is also, for much of the shift, very quiet. The sterile processing department is divided into functional areas. The exact layout varies by facility, but the standard areas are decontamination, inspection and assembly, and sterile storage. These areas are physically separated because they represent different levels of cleanliness, and cleanliness in this department is not a suggestion. It is a gradient carefully maintained from the dirtiest end of the process to the cleanest, and everything moves in one direction. You move in one direction. The instruments move in one direction. Nothing clean goes back to where it was dirty. This is the foundational principle of sterile processing, and also a reasonable approach to life more broadly, though we will not dwell on that. You are a sterile processing technician. Your certification, if you have obtained it, is the Certified Registered Central Service Technician Credential, abbreviated CRCSD, issued by the Healthcare Sterile Processing Association, formerly known as the International Association of Healthcare Central Service Materiel Management. The organization changed its name. The instruments did not change. The instruments are the same instruments they have always been. They will outlast most things. Tonight or today, or whatever shift you are working, you will process surgical instruments through the complete cycle. We will follow you through each step. There are many steps. They are all important. Some of them involve very hot water. Let us begin. You arrive for your shift. The sterile processing department operates around the clock at most acute care hospitals because surgeries do not wait for business hours and instruments do not clean themselves. Your shift begins at 5 in the morning. This is early. You have accepted this. You badge through the department entrance. The department has restricted access because the instruments inside it are either contaminated with biological material or have been rendered sterile. Neither condition benefits from casual foot traffic. The door closes behind you. You proceed to the locker area. In sterile processing, what you wear matters. In the decontamination area, you will wear a different set of personal protective equipment than you wear in the clean assembly area. Both are different from street clothes. Street clothes are not worn in either area. This is a firm rule and not a difficult one. You don your scrubs. Your facility provides scrubs specific to sterile processing. They are not taken home. They are not worn outside the department. They go into the laundry at the end of the shift, and clean ones are provided. This is called a facility laundered scrub program, and it exists because the things you encounter in the decontamination area are things that should not follow you home on your clothing. You check the shift communication board or log. The outgoing shift has noted any outstanding instrument sets, any equipment malfunctions, any priority items requested by the operating rooms for the first cases of the morning. This information is the first thing you read. The first surgical case may begin as early as 7 a.m. You have 2 hours. 2 hours is the right amount of time if nothing goes wrong. You proceed on the assumption that nothing will go wrong, while remaining ready for the several things that might. You note that 3 priority trays have been flagged: a general laparoscopic set, an orthopedic soft tissue tray, and a cystoscopy set needed for a first case urological procedure. These will be processed first. You organize your morning accordingly. You enter the decontamination area. The decontamination area is the receiving and initial cleaning zone of the sterile processing department. It is where instruments arrive after surgical use, contaminated with blood, tissue, saline, lubricants, bone fragments, and other biological and chemical materials that accumulated during the procedure. Your job in this area is to remove all of that. You will do this systematically, using hot water, enzymatic detergents, mechanical cleaning equipment, and, when necessary, manual brushing. You will do this while wearing personal protective equipment sufficient to prevent the contamination from reaching you. You put on your decontamination PPE. This begins with a fluid-resistant gown. The gown is long-sleeved, ties at the back, and extends to mid-calf or below. You put it on. You tie it. It is tied. Next, you put on heavy-duty utility gloves. These are not the thin examination gloves used in clinical areas. They are thick, puncture-resistant gloves that extend past the wrist. Many technicians also wear a second pair of examination gloves underneath, for additional protection in the event that the outer glove is compromised. You wear both. Next, you put on a face shield. The face shield is a clear plastic shield that attaches to a headband and covers the entire face from forehead to chin. You also wear a surgical mask beneath it to protect the mucous membranes of the nose and mouth. Finally, you put on shoe covers. Your shoes are now covered. You are now appropriately attired for the decontamination area. You resemble, in the estimation of no one who has never worked in this department, a scientist of some kind. You are, in a practical sense, a scientist of some kind. Contaminated instruments arrive at the decontamination area via a pass-through window or door from the soiled corridor that connects to the operating room suites. This is a one-way passage. Soiled items come in. They do not go back the way they came. You receive a transport cart containing the used instruments from the first procedure of the previous surgical day. The cart is covered with a blue or red transport drape. You remove the drape and assess the contents. The instruments are in one or more metal perforated trays or rigid containers. They have been grossly decontaminated at point of use in the operating room, meaning the scrub technologist or surgical nurse wiped the instruments down during the procedure to prevent blood and tissue from drying on them, and soaked or kept them moist during transport. Dried biological material is significantly more difficult to remove than fresh biological material. Point-of-use cleaning does not sterilize. It does not even fully clean. It prevents the worst of the drying. The actual cleaning begins now with you. You assess the tray. You identify the instruments. This is a critical step. You need to know what is in the tray in order to clean it correctly, because different instruments have different cleaning requirements. Instruments with lumens, which are hollow channels running through the instrument, require cleaning inside the lumen as well as outside. Instruments with box locks, such as hemostats and needle drivers, must be cleaned with the box lock open, because the hinged joint at the base of the jaws traps debris when closed. Delicate instruments, such as microsurgical forceps with fine tips, must be handled gently to prevent damage. Power instruments with electrical components cannot be fully submerged. You assess the tray. You know what is there. You sort the instruments. Instruments from a single tray are generally processed together, but instruments that require special handling are separated and noted. Sharp instruments, including scissors, osteotomes, and any item with a cutting edge, are handled with heightened caution. Sharp's injuries in sterile processing are a real occupational hazard, and your heavy-duty gloves reduce, but do not eliminate the risk. You handle sharps deliberately, never blindly reaching into a tray, always looking before your hand goes anywhere near a sharp edge or point. You note the instrument count from the case. The operating room should have sent a count sheet, or the count is available in the electronic system, indicating how many instruments were used and how many should be returned. You will verify the count after cleaning. If the count does not match, instruments may be missing, and missing surgical instruments require investigation. Instruments have, on occasion, been left inside patients. This is a wrong outcome. The instrument counting process exists to make it less likely to occur. You participate in this process with appropriate seriousness. You begin manual pre-cleaning at the decontamination sink. The decontamination sink is a large, deep, stainless steel sink, often with two basins. One basin contains a solution of enzymatic detergent in water at the manufacturer's recommended dilution and temperature. other basin contains clean rinse water. You will clean instruments in the first basin and rinse them in the second. Enzymatic detergent contains enzymes that break down the biological materials on instruments. Proteases break down proteins, which constitute the majority of blood and tissue residue. Lipases break down fats. Amylases break down carbohydrates. The combination of these enzymes, applied in solution at the correct temperature, begins the process of digesting contamination from the instrument surfaces. The enzymes require time to work. You do not rush them. You allow appropriate soak times per the detergent manufacturer's instructions. The water temperature matters. Too cold, and the enzymes are not optimally active. Too hot, and the proteins in the biological material can denature, meaning they coagulate and bond more firmly to the surface, which is the opposite of what you want. The recommended temperature for enzymatic cleaning solutions is typically between 60 and 95 degrees Fahrenheit, depending on the specific product. Your facility has a protocol specifying the temperature. You follow it. You submerge the first tray of instruments into the enzymatic solution. You open all jointed instruments. Scissors open. Needle drivers open. Hemostats open. Clamps open. Every joint, every box lock, every hinge is opened before submersion. This is not optional. A closed joint is a hidden surface. A hidden surface is a surface that will not be cleaned. A surface that is not cleaned is a surface that may harbor microorganisms after sterilization. The sterilization process assumes you have cleaned the instrument first. Sterilization of an improperly cleaned instrument is not reliable sterilization. This is called the soil burden, and it is your responsibility to eliminate it before the instrument reaches the sterilizer. Allow the instruments to soak. While they soak, you prepare your cleaning brushes. Instrument cleaning brushes come in many sizes. You select the appropriate brush for the instrument type. A small, fine brush for lumens and cannulas. A medium nylon brush for general instrument surfaces. A larger brush for the jaws of heavy instruments. The brushes are nylon bristled because wire brushes can scratch instrument surfaces, and scratched surfaces are harder to clean and provide a harbor for bacteria. After the appropriate soak time, you begin brushing. You remove the first instrument from the solution while keeping it submerged during brushing, because brushing an instrument above the waterline generates aerosols, and aerosols in a decontamination area are a transmission risk. You brush under the surface of the solution. This is not comfortable. You do it anyway. You brush the jaws of a hemostat with the medium brush. Back and forth, covering all surfaces, paying particular attention to the serrations inside the jaw, which are ridged to grip tissue, and which trap debris in the grooves between each ridge. You count the strokes not because you are required to count them, but because counting is the mind's way of staying present in a task that is repetitive. 7 strokes. 8, 9. The serrations are clean. You move to the box lock. The box lock is where 2 instrument halves pivot together. It looks like 2 interlocking rings with a pin through them. Debris accumulates here even when the instrument is opened, because the geometry of the joint creates small spaces that resist rinsing. You work the brush into the joint, rotating the brush slightly to reach the interior surfaces. You work the instrument open and closed a few times during brushing to expose different surfaces inside the joint. This takes as long as it takes. You move to a laparoscopic trocar. The trocar is a cylindrical device, approximately 12 millimeters in outer diameter and several centimeters long, with a sharp obturator that was used to penetrate the abdominal wall. The obturator is removed and set aside. The trocar cannula has a lumen through which the laparoscope and instruments were passed during the procedure. You select a lumen brush appropriate for the diameter of the trocar. You insert the brush into the lumen and pass it through, pulling it back slightly, then forward again several times. The brush must contact the interior wall of the lumen to clean it. A brush that is too small for the lumen does not contact the walls. A brush that is too large does not pass through. You have selected the correct size. You pass the brush through the lumen 4 times. You inspect the brush after removal. It carries visible material. This is expected. This is what you are removing. You rinse the brush and continue. You clean each instrument in the soiled tray with the same methodical attention. A general surgical tray may contain between 40 and 120 instruments, depending on the procedure type and facility. You have 3 priority trays this morning and several routine trays behind them. You work at a steady pace. Steady is faster than hurried in this department because hurrying produces incomplete cleaning, and incomplete cleaning must be repeated. Repeating cleaning takes more time than doing it correctly the first time. This is true of many things. After manual brushing, you transfer the instruments to the rinse basin. You rinse each instrument thoroughly under running water, working the joints and flushing the lumens. Enzymatic detergent residue on an instrument is not harmful in the quantities that would remain after adequate rinsing, but it can interfere with sterilization by leaving a film on surfaces. You rinse until the water runs clear and free of suds. You place the rinsed instruments in a clean perforated tray for transfer to the automated washing equipment. The manual cleaning step is complete for this tray. You begin on the next. The automated washer disinfector is the central piece of equipment in the decontamination area. It resembles, in a general sense, a very large commercial dishwasher, in the way that a hospital resembles, in a general sense, a hotel. Both comparisons are accurate enough to be useful and inaccurate enough to mislead you if you rely on them too heavily. The washer disinfector processes instruments through a series of automated cycles using hot water, detergents, and heat to clean and thermally disinfect the instruments. Thermal disinfection means using heat to reduce the microbial load on the instruments to a safe level. It does not sterilize. Sterilization comes later. The washer disinfector cleans. The sterilizer sterilizes. They are sequential. They are not interchangeable. Your facility uses a pass-through washer disinfector, which means it has a door on the decontamination side for loading and a door on the clean side for unloading. This design is critical. You load contaminated instruments into the washer from the decontamination area. When the cycle completes, the instruments are unloaded from the other side in the inspection and assembly area, which is a clean area. The instruments move from dirty to clean through the machine without anyone carrying them from one side to the other. This prevents cross-contamination. The two sides are physically separated. You are in the decontamination area. You load the washer from this side. You do not cross to the other side without changing your PPE and going through the appropriate transition area. You load the instrument trays into the washer. Trays are loaded into standardized racks that hold them at angles or flat, depending on the instrument type, to ensure that water and detergent reach all surfaces. Instruments with lumens are placed in specialized lumen cleaning adapters or irrigation manifolds that connect to the washer's spray system and direct pressurized water through the interior channels. You connect each lumen instrument to its adapter. This is a step that cannot be skipped. A lumen instrument placed in the washer without connection to the irrigation system will be cleaned on the outside by spray action, but not on the inside. The inside is where contamination hides in a lumen instrument. The inside is the point. You arrange the instruments in the tray so that they do not nest or overlap. Nested instruments have contact surfaces that the spray arms cannot reach. Instruments that contact each other block cleaning. Every surface must be exposed to the spray. You arrange them with attention. Hemostats open. Scissors open. Everything with a joint is open because you opened all joints during manual cleaning and you are keeping them open now. You load the rack into the washer. You close the loading door. You select the appropriate cycle. Your facility has multiple programmed cycles, one for general surgical instruments, one for delicate instruments requiring lower temperatures, one for powered instruments with longer drainage requirements, one for ophthalmology instruments with specific chemical compatibilities. You select the general surgical cycle for this tray. You press start. The cycle begins. You cannot see inside the washer during operation because the door is locked and the interior is under pressure during certain phases. But you know what is happening inside because you have been trained and because the cycle parameters are documented and because you understand the process even when you cannot directly observe it. The cycle begins with a cold pre-rinse. Cold water flushes loose debris and blood from the instrument surfaces. Cold water is used for this phase rather than hot water because cold water does not coagulate proteins. If you began with hot water, the proteins in the blood residue would denature and bond to the instrument surfaces. The cold pre-rinse sweeps them away before they have a chance to bond. The cold rinse water drains. You cannot see this, but you know it. The cycle advances to the enzymatic wash phase. Enzymatic detergent is automatically injected from the detergent reservoir at the correct concentration. Hot water is added. The wash temperature rises to approximately 60 to to 66 degrees Celsius. The spray arms rotate, directing pressurized detergent solution at all surfaces of the instruments. The cycle timer counts down. The enzymes work. The spray works. The temperature works. These three things work together. The enzymatic wash drains. A hot water rinse follows, removing detergent residue. Then, a second hot water rinse. Then, the thermal disinfection phase. In this phase, the water temperature rises to 93 degrees Celsius, or in some machines to 134 degrees Fahrenheit for a longer dwell time, depending on the A0 value target of the disinfection cycle. The A0 value is a measure of the lethality of a thermal disinfection process, calculated from the time and temperature of exposure, weighted by the temperature's effect on microbial kill rate. A minimum A0 of 60 is required for general medical devices. A minimum of 600 is recommended for heat-stable critical devices. Your washer achieves the target A0 for the cycle you have selected. You know this because the machine is validated and the cycle parameters are documented. You trust the documentation because the documentation is based on testing, and you would not trust it otherwise. The thermal disinfection phase is followed by a drying phase. Heated air circulates through the washer, evaporating residual moisture from the instruments. Moisture on instruments after washing is undesirable for two reasons. It promotes corrosion on instruments not made of fully corrosion-resistant materials, and it can interfere with the packaging and sterilization process. Moisture in a wrapped tray creates conditions that compromise sterilizer performance. The instruments must be dry. The drying phase achieves this. Usually, the cycle is complete. The door on the clean side of the washer releases. You are not on the clean side. A colleague on the clean side will unload the washer, or you will transition to the clean side after removing your decontamination PPE and passing through the transition zone. You transition. You remove your face shield. You remove your gown. You remove your outer gloves. You remove your shoe covers. You wash your hands and forearms with soap and water for the recommended duration. You enter the transition area, where you don clean scrubs if your facility requires a change between areas, or proceed in your original facility scrubs if the protocol permits. You are now entering the clean side of the sterile processing department. The decontamination area is behind you. Nothing from the decontamination area comes with you. This is the rule and also the point. You are in the inspection and assembly area. This is the clean side of the sterile processing department. The air pressure here is positive relative to the decontamination area, meaning air flows from this area toward the decontamination area and not the other way. This is intentional. Airborne contamination from the decontamination side cannot migrate into the clean side against the airflow. The HVAC system enforces this directional boundary invisibly and continuously. The inspection and assembly area is where you will spend the majority of your shift. It is quieter than the decontamination area. It is also brighter. The lighting in the inspection and assembly area must be sufficient for close visual examination of instrument surfaces. Dim lighting would cause you to miss defects. You are not going to miss defects. The lighting is bright. You receive the washer disinfected instruments from the unloading side of the pass-through washer. You place them on the inspection table. The inspection table is a large, illuminated work surface, stainless steel, with task lighting overhead, and often a lighted magnifying lens mounted on an articulating arm for examining fine instrument details. You position your instruments. You begin inspection. Inspection serves two purposes. The first purpose is cleanliness verification, confirming that the cleaning process successfully removed all visible soil from every instrument surface. The second purpose is functional and physical assessment, confirming that each instrument is in correct working condition, free of defects, damage, or where that would impair its performance or compromise patient safety. You pick up the first instrument. It is a cryohemostat, a type of locking clamp used to occlude blood vessels or grasp tissue. It is 6 inches long, curved, with serrated jaws and a box lock. You hold it under the task lighting. You examine the jaws. They are clean. You can see no organic residue in the serrations. You close the jaws and examine the alignment. The jaws meet evenly across their full length. Misaligned jaws indicate that the instrument has been dropped, bent, or damaged. These jaws are aligned. You open the instrument fully and examine the box lock under the magnifying lens. The box lock surfaces are clean. There is no pitting, no corrosion, no cracking. You release the ratchet and work the instrument open and closed 3 times, listening and feeling for smooth action. It opens smoothly. It closes smoothly. The ratchet engages at each position with a clean click. You examine the ratchet teeth under magnification. They are not worn. The tips of the jaws are examined. They are intact, not bent or splayed. You pass the inspection. You set it aside in the clean assembly tray. You pick up a pair of Metzenbaum scissors. Metzenbaum scissors are delicate, fine-pointed scissors used for dissection of tissue in surgery. They have long, slender shanks and relatively short, narrow blades. They are among the instruments most vulnerable to damage from improper handling, including rough cleaning, incorrect sharpening, or contact with harder instruments during storage or processing. You examine the blades under magnification. The cutting edges must be sharp and continuous, without nicks, chips, or rolls in the edge. You hold the scissors up to the task light and sight along the cutting edge. It is straight and smooth. A nick in a scissor blade appears as a small dark interruption in the continuous bright reflection of the edge under light. There is no nick. You cut a small piece of test gauze. The gauze is cut cleanly, with no dragging or snagging. The scissors function correctly. You set them aside. You pick up a laparoscopic grasper. This is a long, thin instrument, approximately 30 centimeters in length, designed to pass through a laparoscopic trocar cannula. It has a handle with a ratcheting mechanism at the proximal end and jaw inserts at the distal end. It has an insulating sheath for electrosurgical use. You inspect the insulation. Insulation on electrosurgical instruments is critical. A defect in the insulation, a crack, a pinhole, a worn area, can allow electrical current to escape at an unintended location during surgery, causing an internal burn to adjacent tissue that the surgical team cannot see and will not detect until it manifests as a complication postoperatively. You examine the insulation under magnification and also with a dedicated insulation testing device which detects electrical leakage through defects that may not be visible. You attach the instrument to the tester. You run the test. The indicator shows no leakage. The insulation is intact. You examine the jaw mechanism of the grasper. You actuate the handle. The jaws open and close fully and smoothly. You inspect the jaws for surface damage, corrosion, and debris. The jaw faces have a fine cross-hatched pattern for gripping tissue. Each small diamond of the pattern is present and undeformed. The jaws close flush and parallel. The instrument passes. Instrument inspection also includes a check for residual moisture. Instruments emerging from the washer drying cycle should be completely dry. If an instrument is still damp after the drying cycle, this can indicate that a lumen was not fully purged of water, or that the instrument was incorrectly loaded. You check the lumens of the laparoscopic instruments by blowing a brief puff of clean, compressed air through each channel and observing for moisture droplets. No droplets are present. The instruments are dry. Some instruments fail inspection. This happens regularly. A hemostat with a sprung box lock, one where the pivot has loosened and the joint has excessive play, fails inspection and is tagged for repair. A needle driver with worn tungsten carbide jaw inserts, visible under magnification as smoothed, shiny areas where the carbide has abraded away, reducing the instrument's ability to grip a suture needle securely, fails inspection, and is tagged for re-tipping or replacement. A scissors with a rolled edge, where the fine cutting edge has folded microscopically inward and requires resharpening, fails inspection, and is set aside for the instrument sharpening service. Failed instruments are not returned to the surgical instrument tray. They are segregated, tagged with a description of the defect, and sent for repair or replacement through the facility's instrument repair process. The surgical team will work with a substitute instrument or with the set minus the defective item until the repair is completed. A defective instrument that passed inspection and entered surgery is a problem. A defective instrument that was caught during inspection is a process working correctly. You complete inspection of the laparoscopic tray. Out of 22 instruments, one fails. A clip applier with a damaged jaw alignment mechanism that causes the clip to deploy asymmetrically. It is tagged. You make a note. You have 21 instruments proceeding to assembly. You verify this against the count sheet. 21 is the correct count for the past instruments. The failed instrument is logged and will be communicated to the operating room so that a substitute can be sourced for the first case if needed. You proceed to inspect the orthopedic soft tissue tray. Orthopedic instruments are, in general, larger and more robust than general surgical instruments. They include larger retractors, elevators, curettes, and the assorted heavy hardware of orthopedic soft tissue work. Many are solid metal with fewer moving parts than general surgery instruments. Their inspection focuses on surface integrity, edge condition where applicable, and freedom from corrosion or pitting. Corrosion in surgical instruments appears in several forms. Rust, which is iron oxide, appears as reddish-brown discoloration, or pitting on instruments made from lower grades of stainless steel or instruments that have been scratched or damaged in ways that expose the underlying metal. Water spotting, a different phenomenon, appears as white or gray mineral deposits from the dissolved minerals in the rinse water, and is not corrosion, but is an indicator of inadequate drying or water quality issues. True pitting corrosion appears as small depressions in the metal surface, the result of electrochemical attack. Any of these findings are noted, and the instrument is assessed for whether the condition affects function or patient safety. Surface water spots are generally cleaned with an appropriate stainless steel instrument cleaner. Pitting, or active rust, results in the instrument being removed from service. You work through the orthopedic tray. It is a large tray. It takes time. You are not in a hurry. You are thorough. The instruments pass. They are set aside for assembly. Before assembly, jointed instruments are lubricated. Instrument lubricant is a water-soluble, non-toxic, non-silicone lubricant, specifically formulated for surgical instruments. It is sometimes called instrument milk because it is typically a thin, white, or milky solution in which instruments are briefly dipped or sprayed. The lubricant reduces friction at joints and box locks, preserving smooth function and extending the instrument's working life. It also provides a degree of protection against surface corrosion. By forming a very thin barrier on the metal surface, the lubricant must be water-soluble because it must be compatible with the sterilization process. A non-water-soluble lubricant, such as a petroleum-based oil, would not be penetrated by steam during sterilization and would shield the instrument's surface from the sterilizing agent. This would be a significant problem. The purpose of the lubricant is to protect the instrument. The purpose of sterilization is to make the instrument safe for patient use. These two purposes must not conflict. Water-soluble instrument lubricant is designed specifically so that they do not conflict. The steam penetrates and sterilizes. The lubricant does its job and is then removed or displaced by the sterilization process without interfering. You prepare the lubricant bath. Your facility uses a dip system, a container filled with diluted instrument lubricant solution at the manufacturer's recommended concentration. You submerge jointed instruments in the lubricant bath for the recommended contact time. Usually 30 to 60 seconds is sufficient. You work the joints of each instrument while they are submerged, moving the box locks open and closed several times to ensure the lubricant works into the joint mechanism. You remove the instruments from the lubricant bath. You do not rinse them. Rinsing would remove the lubricant. You allow excess lubricant to drip off. The instruments are set on a clean towel or rack to drain briefly before assembly. They glisten slightly. This is acceptable. Excessive lubricant that pools in the tray during autoclaving is also acceptable and is not a contamination concern. The autoclaving process handles it. Not all instruments are lubricated. Instruments with no moving parts do not require lubrication. Scissors may or may not be lubricated depending on their design and facility protocol. Instruments with plastic or rubber components may not be compatible with certain lubricant formulations. You know which instruments in each tray require lubrication, because this is part of your training, and because your facility's instrument assembly instructions include this information for each standardized tray. Assembly is the process of placing the inspected, lubricated instruments back into their trays in the correct configuration for sterilization and surgical use. Every standardized instrument tray in the sterile processing department has an assembly guide. The assembly guide is a document, often laminated and affixed near the assembly station or available in a digital system, that shows the correct placement of every instrument in the tray, which instruments go in which position, in which orientation, in what order, and how many of each. The assembly guide exists because a surgical instrument set is not merely a collection of instruments. It is a precisely defined kit that the surgical team depends on to contain everything they need for a specific procedure. An incorrect assembly, one where an instrument is missing, duplicated, or replaced with a wrong instrument, can disrupt a surgical case. You open the assembly guide for the laparoscopic general surgery set. The guide shows a diagram of the tray with each instrument's position labeled. You follow it. Tray is a perforated stainless steel tray with a locking lid. The perforations allow steam to circulate through the tray during sterilization. A non-perforated tray would trap air inside, and trapped air is the enemy of steam sterilization. Trapped air creates a barrier between the steam and the instrument surface, preventing the steam from contacting the surface, and steam contact is how steam sterilization works. Perforations allow air to be displaced by steam. The perforated tray is not a preference. It is a requirement. You place the instruments into the tray according to the guide. Heavier instruments go in the lower levels or on the bottom of the tray. Delicate instruments go on top, where they will not be crushed by heavier items. The principle is, nothing heavy rests on something delicate. This is sensible and easy to remember. Scissors are placed with the tips pointing in a consistent direction, typically toward one end of the tray, and with a protective tip cover or silicone tip mat if your facility uses them. Tip covers are small rubber or plastic caps that fit over the scissor tips and prevent the sharp points from contacting other instruments during sterilization and storage. A bare scissor tip pressing against another instrument under the pressure of a full tray may cause damage to both. Tip covers prevent this. Retractors, which are wide, flat, or curved instruments used to hold tissue away from the surgical field, are arranged flat in the tray. Handheld retractors, unlike self-retaining retractors with ratchet mechanisms, have no moving parts and require only placement, not any specific orientation. You place them flat, stacked no more than 2 deep, with the handles oriented consistently. Needle drivers and hemostats are placed in the open position. You will say this again. Jointed instruments are placed in the open position. Open, not closed. If placed closed, the jaws and box locks are hidden from the steam during sterilization. If the joints are open, every surface is exposed. You have opened every jointed instrument, every single one. They are open. They will remain open throughout sterilization. Laparoscopic instruments are placed on a specialized rack, or with their lumens oriented to facilitate steam contact inside the channels. Some facilities use a specific laparoscopic instrument organizing system that holds each instrument vertically or at an angle with its distal end elevated, allowing gravity to assist in steam penetration of the lumen. You arrange them per the assembly guide. You count the instruments as you place them. You are counting against the assembly guide's count. 14 hemostats. 14 hemostats are now in the tray. 4 retractors. 4 retractors are in the tray. 3 needle drivers. 3 needle drivers are in the tray. You count each category as it is placed. When the tray is complete, you do a final count of the entire tray. The count matches the assembly guide. The tray is correctly assembled. You place the count sheet or a documentation record with the assembled tray, or you record the completed assembly in the electronic instrument tracking system, whichever your facility uses. The tracking system records who assembled the tray, when it was assembled, what instruments it contains, and will subsequently record the sterilizer load it goes into, the sterilization cycle parameters, the expiration date of the sterility, and its delivery location. This traceability is regulatory and also practical. If a sterilization failure is identified after the fact, the tracking system allows rapid identification of which trays were in the affected load and where they went. This is called recall. You hope it is never used. It exists in case it is needed. You assemble the second priority tray, the orthopedic soft tissue set, following its assembly guide. You assemble the cystoscopy set. Cystoscopy instruments include the rigid cystoscope body, the obturator, the bridge, the working elements, light post adapters, and associated irrigation components. They are delicate optical instruments. The cystoscope contains a lens system. You handle it with particular care. You do not drop it. Dropping a cystoscope damages the lens system, which is expensive to repair and time-consuming to send out for service. You do not drop it. You place it in the tray with the protective padding provided in the cystoscopy tray set. 3 priority trays are assembled. You set them aside for packaging. Before instruments can be sterilized, they must be packaged. The packaging serves two functions. It allows the sterilizing agent to reach the instruments during sterilization, and it maintains the sterility of the instruments after sterilization until the package is opened in the sterile field of the operating room. These are related but distinct functions. The primary packaging systems used in sterile processing are wrapping and rigid containers. Your facility uses both. Wrapping involves enclosing the instrument tray in one or more layers of sterilization wrap. Sterilization wrap is not ordinary fabric or plastic. It is a non-woven material, often a polypropylene-based product, that is porous enough to allow steam or other sterilizing agents to pass through it during the sterilization cycle, while being dense enough to act as a barrier against microbial penetration after sterilization. A sterilized package wrapped in proper sterilization wrap and stored correctly in a clean, climate-controlled environment maintains sterility, not based primarily on a fixed time limit, but based on a ventilated sterility, meaning sterility is maintained until the package is compromised by a specific event: opening, tearing, wetting, contamination, or other breach. This concept is called a ventilated sterility maintenance. You wrap the laparoscopic tray using the sequential wrap method. This is one of two standard wrapping techniques, the other being the simultaneous wrap or envelope fold. In the sequential wrap method, you wrap the tray in one layer of sterilization wrap, then wrap the entire wrapped package in a second layer. Two layers provide double protection for the sterile barrier. If the outer wrap is torn or compromised during storage or transport, the inner wrap may still be intact. You lay a square of sterilization wrap on the flat assembly table, oriented diagonally like a diamond. The tray goes in the center. You fold the nearest corner of the wrap up over the tray. You fold the far corner up. You fold the left corner in, tucking it under the tray slightly. You fold the right corner in. You fold the remaining corner up and over the top of the package. You secure the folded corners with autoclave tape. Autoclave tape is a paper tape with chemical indicator stripes. The chemical indicator stripes are pale yellow cream before sterilization. They turn dark brown or black after exposure to steam sterilization conditions. The color change of the autoclave tape tells you, and anyone handling the package afterward, that the package has been through a sterilization cycle. It does not confirm that sterilization was achieved. It confirms only that the package was exposed to conditions that should produce sterilization. This distinction is important, and we will return to it. You repeat the wrap with a second layer. The package is now double wrapped. It is set aside. The orthopedic soft tissue tray is processed in a rigid sterilization container system. Rigid containers are reusable metal or polymer containers with a locking lid and filter elements in the lid and base. The filter elements serve the same purpose as the wrapping material. They allow the sterilizing agent to enter and exit the container while providing a bacterial barrier after sterilization. The rigid container is placed on the autoclave rack. After sterilization, the lid is locked and the container is sealed. The filter elements are inspected before use. A compromised filter is a compromised sterile barrier. You load the instruments into the rigid container. You verify the filter elements are seated correctly in the lid and base. You close the lid. The container latches. You attach a container label with the tray name, contents, sterilizer load number to be assigned, and assembly date. You apply a chemical indicator label to the container. Rigid containers often use internal chemical indicators placed inside the container rather than on the outside to provide evidence that the sterilizing conditions were achieved inside the container rather than merely on its exterior. You label each package with the required information: tray name, lot control number, sterilizer identification, cycle number, and the date of sterilization. These labels are generated by the instrument tracking system or completed manually per your facility's protocol. Every package leaving sterile processing is labeled. A package without a label cannot be used because a package without a label cannot be verified as sterile, cannot be traced if a recall is necessary, and cannot be confirmed as the correct instrument set. Labels are not bureaucracy. Labels are accountability. The cystoscopy set is packaged in a peel pouch. Peel pouches are flat, flexible pouches with one side of clear plastic film and the other side of a porous paper or Tyvek material. The paper or Tyvek side allows steam penetration. The clear side allows visual inspection of the instrument inside without opening the package. The pouch is sealed by peeling apart a pre-sealed edge and pressing it together on a heat sealer, or by folding and pressing a self-seal adhesive strip. The seal must be complete and continuous. Any breach in the seal is a breach in the sterile barrier. You place the cystoscope components in appropriately sized peel pouches, 1 or 2 instruments per pouch, depending on size, ensuring that the instruments do not contact the seal area, that there is adequate room inside the pouch for steam circulation, and that sharp tips are protected or oriented so they cannot puncture through the pouch. A punctured peel pouch is an open package and is not sterile. Sterilization is the process of eliminating all viable microorganisms, including bacterial spores, from the instrument surface. This includes bacteria, viruses, fungi, and prions, with the exception that prion decontamination requires specialized processing beyond standard sterilization cycles. The standard against which sterilization processes are measured is a sterility assurance level, or SAL, of 10 to the -6, meaning that the probability that a single viable microorganism survives the sterilization process on any given item is 1 in 1 million. This is not 0. 1 in 1 million is considered an acceptable risk for medical devices. It is a very small risk. It is also not 0. You find this information neither alarming nor comforting. You find it accurate. Your facility uses steam sterilization as the primary method for heat-stable instruments. Steam sterilization, also called autoclaving, uses saturated steam under pressure to achieve sterilizing temperatures. The steam carries heat energy more efficiently than dry heat and penetrates porous packaging materials effectively. It is the most widely used, most reliable, and most economical method of sterilization for instruments that can withstand the temperatures and moisture involved. Not all instruments can. Heat-sensitive items, including certain plastics, optical components bonded with heat-sensitive adhesives, and powered instruments with sensitive electronics, require low-temperature sterilization methods such as ethylene oxide gas, hydrogen peroxide gas plasma, or peracetic acid liquid sterilization systems. You are working with heat-stable instruments this morning. You will use the steam sterilizer. The steam sterilizer in your department is a large, rectangular chamber made of heavy stainless steel, front-loading, with a thick door that seals by means of a gasket and a locking mechanism. The chamber interior is approximately the size of a large filing cabinet, though this varies by model. Your department has multiple sterilizers to handle the volume of instrument processing required by the surgical schedule. You are loading the primary cycle sterilizer. Before loading, you perform the daily sterilizer verification tests. These are tests performed every day that the sterilizer operates before the first processed load to confirm that the sterilizer is functioning correctly. The tests include the Bowie-Dick test, also called the air removal test, which verifies that the sterilizer is correctly evacuating air from the chamber before introducing steam. Air in the chamber is a problem because air pockets prevent steam from contacting instrument surfaces. The Bowie-Dick test uses a standardized test pack containing a chemical indicator sheet. If the sterilizer correctly removes air and achieves uniform steam penetration, the indicator sheet shows a uniform color change across its entire surface. An uneven change, or a failure to change in the center of the pack, indicates an air removal problem. The test result this morning is a uniform change. The sterilizer passes. You load the sterilizer. Packages are loaded on the sterilizer racks with space between them, never packing them tightly together. The space between packages allows steam to circulate. Steam must reach every package surface. Packages stacked or touching reduce steam circulation. You place the double-wrapped laparoscopic tray on the lower rack. The rigid container is placed on a separate rack. Peel pouches are placed in a pouch rack that holds them vertically with the paper side down. Because steam enters through the paper side and condensate can drain downward rather than pooling inside the pouch. You close the sterilizer door. You select the appropriate cycle. The standard cycle for wrapped trays and rigid containers is the gravity displacement cycle, or more commonly, the pre-vacuum or dynamic air removal cycle. The dynamic air removal cycle, sometimes called pre-vacuum, uses a series of pulses of vacuum and steam injection to remove air from the chamber. And from within the packages, before the sterilization phase begins. It is more effective at air removal than the gravity cycle and is preferred for porous loads, wrapped trays, and rigid containers. You select the pre-vacuum cycle. The cycle parameters for a standard pre-vacuum cycle at your facility are pre-vacuum pulses to remove air, steam injection to achieve the sterilization temperature of 132 to 134 degrees Celsius, an exposure time of 4 minutes at temperature, followed by an exhaust phase and a drying phase. 4 minutes at 132 degrees Celsius in saturated steam is sufficient to achieve the required sterility assurance level for a properly cleaned and packaged load. The temperature must be maintained throughout the exposure phase. A single degree drop in temperature during the exposure phase changes the sterilization math. The sterilizer is designed to maintain the temperature. It does. The temperature is monitored continuously by sensors inside the chamber and logged by the sterilizer's recording system. You press start. The cycle initiates. The door locks. The pre-vacuum phase begins. You hear the mechanical sounds of the sterilizer, the vacuum pump engaging, the pulses of steam, the pressure changes. These sounds are the background of your department during the processing hours of every surgical day. You have heard them so many times that you no longer consciously hear them unless they change, in the way that any reliable sound becomes invisible until it is absent or wrong. If the sterilizer made a different sound, you would notice. It does not make a different sound. Everything is proceeding normally. The pre-vacuum phase completes. The sterilization phase begins. Steam fills the chamber. The temperature rises to the set point. The exposure timer begins. 4 minutes. You attend to other tasks during the cycle because you have other trays to process. You keep an awareness of the sterilizer cycle. This is not difficult. The machine will alarm if the cycle is disrupted. The exposure phase completes. The exhaust phase begins, releasing steam pressure from the chamber. The drying phase begins, drawing heated air through the chamber to evaporate residual moisture from the packages and instruments. A wet pack emerging from the sterilizer is a failed pack. Moisture compromises the sterilization barrier because moisture carries microorganisms. If a package is wet when it emerges, the sterilization cycle is considered incomplete and the pack must be reprocessed. The drying phase prevents this. It takes time. You do not reduce the drying time. Reducing the drying time produces wet packs. Wet packs must be reprocessed. Reprocessing takes more time than completing the drying cycle. You complete the drying cycle. The cycle ends. The door releases. You open it. A rush of warm air carries the particular smell of sterilized instruments, which is a clean, slightly metallic, heated steam smell that is entirely distinctive and has no good analogy outside of sterile processing departments. You have smelled it enough times that it means only one thing to you, which is that a cycle has completed. You examine each package before removing it from the sterilizer. You are looking for wet packages, torn or compromised wrapping, filter elements dislodged from rigid containers, and any visible signs of cycle disruption. You also check the autoclave tape chemical indicators on each package. They have changed color. Pale yellow cream before the cycle, dark brown now. The color change confirms exposure to sterilizing conditions. You check the internal chemical indicator in the rigid container. It has also changed. All packages are dry. All indicators have changed. All packages are intact. You remove the packages from the sterilizer. You place them on a cooling rack, away from drafts and traffic. Packages should be allowed to cool before handling and storage. Warm packages from the sterilizer are more vulnerable to damage because the packaging materials are slightly softened by the heat and moisture of the cycle. Placing a warm package on a cold surface can cause condensation inside the package. You allow the packages to cool. This takes approximately 30 minutes for larger trays, less for peel pouches. Chemical indicators tell you that a package was exposed to sterilizing conditions. They do not tell you that sterilization was achieved. There is a difference. The difference is the biological indicator. A biological indicator is a standardized preparation of bacterial spores, the most resistant form of microbial life, used to challenge the sterilization process. If the sterilization cycle is effective, the spores are killed. If the spores survive, the sterilization process failed. This is the most direct test of sterilization efficacy available. The spores used in biological indicators for steam sterilization are Geobacillus stereothermophilus spores, formerly classified as Bacillus stereothermophilus. These spores are specifically chosen because they are highly resistant to steam sterilization, more resistant than any pathogen you are likely to encounter on a surgical instrument. If the sterilization cycle kills G. stereothermophilus spores, it has killed everything less resistant, which is everything else. Biological indicators are run in every sterilizer load at some facilities, in every load of implantable devices at all facilities per regulatory requirement, and at minimum weekly at all facilities. Your facility runs biological indicators daily in at least one sterilizer load and in every implant load. This morning's load did not contain implants. The biological indicator test for the day's first cycle was placed in a test pack, a standardized collection of towels or wrapping material assembled to the dimensions specified in the testing protocol, which was included in the load. You retrieve the biological indicator from the test pack. It is a small, self-contained vial containing the spore preparation and a culture medium. The culture medium is physically separated from the spores inside the indicator during sterilization. After the cycle, you crush the indicator vial to break the internal ampule, releasing the culture medium to mix with the spore preparation. If any spores survived, they will grow in the culture medium and change its color from purple to yellow over the incubation period. If no spores survived, the medium remains purple. You place the incubated biological indicator in the biological indicator incubator, a small, precise incubator set to the growth temperature optimal for G. stereothermophilus, approximately 55 to 60 degrees Celsius. You also place an untested biological indicator from the same lot in the incubator as a positive control to confirm that the culture medium and spores in the lot are viable and capable of growing if the sterilization had not occurred. Both indicators incubate. The incubation period is 1 to 3 hours for rapid readout biological indicators, which most modern facilities use, or 24 hours for conventional biological indicators. Your facility uses rapid readout indicators. In approximately 2 hours, you will read the result. If the test indicator remains purple and the control indicator turns yellow, the sterilization cycle is confirmed as effective. If both turn yellow, or the test indicator turns yellow, there is a potential sterilization failure, and you initiate your facility's recall and investigation protocol. The result this morning, when you check it at 10:30, will be purple for the test and yellow for the control. You already know this, not because you have checked it, but because you have run this test many times, and the results are virtually always what they should be. Because the sterilizer is maintained and validated, the instruments are properly cleaned, the loads are properly configured, and the process is followed correctly. This does not make the testing unnecessary. The testing is how you know. Knowing is the point. The cooled, sterilized packages move from the cooling rack to sterile storage. Sterile storage is a defined area of the sterile processing department, or a designated storage room with controlled conditions. The conditions required are a temperature between 64 and 75 degrees Fahrenheit, a relative humidity between 35 and 70%, and positive air pressure relative to adjacent areas. These conditions maintain the integrity of the sterilization wrap and minimize environmental factors that could compromise the sterile barrier. Packages are stored on open wire shelving, not in closed cabinets. Closed cabinets can trap moisture and do not allow air circulation. Open wire shelving allows air to circulate around all package surfaces. The shelving is at least 8 to 10 inches from the floor to avoid contamination from floor-level activity, and at least 2 inches from exterior walls to avoid condensation from temperature differentials near exterior building walls. Packages are arranged on the shelves with older stock in front and newer stock behind. This is the first in, first out principle, or FIFO. The purpose of FIFO in sterile storage is not the same as in food storage. A sterilized instrument package does not expire in the way that food expires. Sterility is event-related, not time-related, as established earlier. But FIFO is still practiced because it minimizes the chances of packages being stored for extended periods, during which their packaging could be subject to repeated handling and potential compromise. A package that sits at the back of a shelf for 2 years, while newer packages are retrieved from the front, accumulates more opportunity for incidental damage than one that moves through storage in normal rotation. You place the sterilized trays in their designated locations on the shelving. Each tray type has a designated location labeled on the shelf. The laparoscopic general surgery set goes here. The orthopedic soft tissue set goes here. The cystoscopy set will be delivered directly to the operating room rather than stored, because it is a priority item for this morning's first case. You transport the cystoscopy set to the operating room via the clean corridor. The clean corridor is the distribution route for sterile items. It is separate from the soiled corridor, through which contaminated instruments travel to the sterile processing department. Items travel from sterile processing to the operating room through the clean corridor. Used instruments travel from the operating room to sterile processing through the soiled corridor. The two corridors do not intersect. The system is directional. Clean to dirty, then dirty back to clean through the processing cycle, then clean again to the surgical suite. It circles. It does not stop. You arrive at the operating room. You deliver the cystoscopy set to the sterile supply room adjacent to the OR suites. You verify the package labels against the case cart request. The set name matches. The sterilization lot number is current. The chemical indicator on the package shows appropriate color change. The package is intact and dry. You hand it off to the OR technologist. You return to sterile processing. The sterile processing department does not have a beginning and an end in the way that a discrete project has a beginning and an end. It has a cycle. The cycle turns. Instruments leave the operating room contaminated. They arrive in sterile processing. They are cleaned, inspected, assembled, packaged, and sterilized. They are stored or delivered. They are used. They return contaminated. The cycle turns again. Throughout the morning, as the surgical schedule progresses, soiled instruments continue to arrive at the decontamination area from completed cases. You and your colleagues process them as they arrive, prioritizing the sets needed for upcoming cases. The operating rooms are running several cases simultaneously, which means the demand on sterile processing is simultaneous rather than sequential. You triage. The hip replacement tray, needed for the 11 o'clock orthopedic case, goes ahead of the general abdominal tray from a case that completed 2 hours ago and is not needed again until afternoon. Prioritization is a constant, low-level cognitive task running beneath the procedural work. You receive a tray from a laparoscopic cholecystectomy that completed at 9:45. A cholecystectomy is the removal of the gallbladder. The tray contains instruments that have been used in an abdominal cavity and are contaminated with bile in addition to blood and tissue. Bile is a digestive fluid produced by the liver. It is yellow-green. It is not pleasant to encounter in volume. It is, however, simply another biological substance that enzymatic detergent and hot water will address. You process the tray with the same method as any other. The instruments do not care what they have been through. They are instruments. you receive a call from the orthopedic operating room. The surgeon has requested an additional instrument not included in the standard soft tissue tray, a specific bone hook that the surgeon prefers for this patient's procedure. The instrument is in sterile storage, already sterilized as part of a supplemental orthopedic instrument set. You locate it. You verify the package integrity and indicator. You send it to the OR via the clean corridor. This kind of individual instrument or supplemental item request is routine. It is not a disruption of your process. It is part of your process. At 11 a.m., you perform your next sterilizer cycle. You have a full load, 5 instrument trays, and a case cart of peel pouches containing supplemental instruments. You load the sterilizer using the same configuration principles as the first load. You run the pre-vacuum cycle. The cycle completes. Packages are dry. Indicators have changed. Load is documented. Packages go to cooling rack. You conduct a routine check of the sterile storage area at 11:30. This is a periodic inspection to verify that stored packages have not been disturbed, compromised, or allowed to become wet or contaminated. You walk the storage shelves. You examine packages at the front of each shelf for visible damage, wet spots, or tears. You note no issues. Storage is intact. You check the biological indicator from the morning's first load. It has been incubating for approximately 2.5 hours. The rapid readout indicator displays its result. The test indicator is purple. The positive control is yellow. The sterilization cycle is confirmed as effective. You document the result in the sterilizer log, noting the sterilizer number, the cycle number, the lot number of the biological indicator, the incubation time, and the result. This documentation is part of the permanent record of each sterilization load. It is retained in accordance with your facility's document retention policy, which is determined by regulatory requirements and typically runs to a minimum of 3 to 10 years. You process a set of powered surgical instruments. Powered instruments include battery-operated or pneumatic drills, saws, and reamers used in orthopedic and neurosurgical procedures. These instruments require special handling in sterile processing because their internal mechanisms, batteries, and electronic components limit the cleaning and sterilization methods that can be safely used on them. The manufacturer's written instructions for use, called IFU, specify exactly how the instrument must be cleaned, what products are compatible with it, what sterilization method and cycle parameters are appropriate, and what parts must be disassembled before processing. You consult the IFU for each powered instrument you process. You do not deviate from the IFU. The IFU is the documentation provided by the manufacturer based on validation testing of the specific device. A cleaning or sterilization method not validated for a device is not confirmed to be effective on that device. You follow the IFU. The powered instruments for this procedure were used with a pneumatic handpiece. The handpiece is disassembled per the IFU. The attachments, including the drill bit chuck, the irrigation ports, and the motor housing, are cleaned per the specific instructions for each. Lumens in the irrigation ports are flushed and brushed per the IFU's specified brush size and technique. The handpiece is reassembled per the IFU. It is packaged in the rigid container specified for that instrument. It is sterilized in the appropriate cycle specified in the IFU. All of this is documented. Lunch occurs at some point during the middle of the shift. You leave the department for your break and return. This is a normal feature of a shift. The instruments do not take a break. The instruments wait, correctly staged at whatever phase of processing they were in when you left. The process resumes when you return. This is fine. The process is designed for this. The afternoon portion of the shift handles the instruments from the afternoon surgical cases and processes any specialty sets that did not come up in the morning. Specialty sets are instrument trays configured for less common procedures. Where a general laparoscopic tray may be used dozens of times per week, a specialty tray for, say, a posterior spinal fusion with instrumentation, or a total hip arthroplasty with all associated trials and implant insertion tools, may be used once or twice per week or less. Specialty sets are often larger, more complex, and more expensive. They may include precision instruments with specific handling requirements, implant components that require special sterilization documentation, and items that come from external sources, such as instrument loan sets provided by surgical device manufacturers for cases involving their proprietary implant systems. A loaner instrument set is a tray of instruments typically owned by a surgical device company that is sent to the hospital for a specific surgical case and must be returned to the company afterward. Loaner sets present particular challenges in sterile processing. They arrive from outside the hospital, sometimes with documentation, and sometimes without sufficient documentation. They must be processed using the manufacturer's IFU for the specific instruments, which may be different from the IFUs for instruments your department normally handles. They must be processed in time for the scheduled surgical case. They must be correctly counted, documented, and ultimately returned in the condition they were received. A loaner set arrives this afternoon for tomorrow morning's spinal case. You receive it. You verify the delivery documentation. You inventory the contents against the packing list. The packing list shows 47 items. You count 46. One item, a specific trial implant sizer, is missing. You contact the company representative immediately and document the discrepancy. The representative will provide the missing item before tomorrow's case. You process the 46 items that are present, clearly noting in the tray documentation that one item is missing and will be received and processed separately. This documentation will follow the set through sterilization and into the operating room, where the surgical team will be aware of the status. Transparency is not a preference in sterile processing. It is a requirement. You process a tray that has been flagged with a potential cleaning quality issue. A colleague noticed during inspection that a trocar cannula from a previous case has visible residue inside the lumen that was not cleared by the initial processing. This tray was quarantined, meaning it was set aside and not allowed to proceed through packaging and sterilization until the issue was resolved. You return the tray to the decontamination area for reprocessing. You re-clean the trocar lumen manually with the appropriate brush and enzymatic solution. You rerun the tray through the washer disinfector. You reinspect the lumen after the second cleaning. It is now clean. You document the reprocessing event, including the reason and the corrective action. The tray proceeds. This process added time. The time was necessary. Reprocessing events are documented and tracked not as disciplinary records, but as quality data. If a particular instrument type is frequently flagged for inadequate cleaning after initial processing, this is a signal. The cleaning protocol for that instrument type may need revision. The brush specifications may need updating. The point of use care in the operating room may need improvement. Or the washer disinfector may need to be assessed for performance issues with that load configuration. Reprocessing data generates improvement. You participate in generating it accurately. At 3 p.m., you run your final sterilizer load of the shift. The load contains trays assembled for tomorrow morning's first surgical cases. Tomorrow's team will arrive to find a portion of the morning's instruments already processed and stored. This is how the overnight work of sterile processing supports the daytime work of the surgical suite. Your shift's output supports tomorrow's patients. You do not think about this constantly, but it is true continuously. Before your shift ends, you complete the equipment maintenance checks and documentation required at the end of each processing day. You clean the washer disinfector. The interior chamber of the washer is cleaned and inspected daily. You open the door and examine the spray arms. The spray arms are the rotating assemblies inside the washer that direct water at the instruments. The spray arm nozzles are small holes that must be clear and unobstructed for uniform water delivery. You remove the spray arms per the manufacturer's instructions, inspect the nozzles, and clear any mineral deposits or debris with a small probe. You reinstall the spray arms. You inspect the washer's filter screen. The filter screen catches debris washed from instruments during the cleaning cycle, preventing it from recirculating and redepositing on instruments. If the filter screen becomes clogged, the washer's drainage and circulation is impaired. You remove the filter screen. There is accumulated debris. This is expected. You dispose of the debris appropriately as contaminated waste. You clean the filter screen. You reinstall it. You drain and clean the enzymatic detergent basin if your department uses a separate pre-soak sink. Fresh enzymatic solution cannot be saved from one shift to the next. Enzymatic activity degrades over time, and a solution that has been used for a shift's worth of contaminated instruments is contaminated itself. You drain it. You clean the basin. Tomorrow's shift will prepare fresh solution. You wipe down the inspection and assembly tables with an appropriate disinfectant wipe. The assembly area is a clean area, but it is not sterile, and surfaces accumulate environmental contamination over the course of a shift. Daily surface disinfection maintains the appropriate cleanliness level of the area. You complete the sterilizer daily log. Every sterilizer cycle run today is recorded. The time, the cycle type, the load contents by lot number, the temperature and time achieved, the physical indicator readings from the sterilizer printout, the chemical indicator results, and the biological indicator result. This log is the sterilizer's accountability document. If there is ever a question about whether an instrument in a specific case was properly sterilized, the sterilizer log is where the answer is found. You complete it accurately and in full. Complete the department's shift record. This includes the name and schedule of each technician on shift, the number of instrument trays processed, any equipment malfunctions or deviations from protocol, any quarantined items, any reprocessing events, any loaner set discrepancies, and any items of communication for the incoming shift. This record is the shift's accountability document. It is reviewed by supervisory staff and retained as a record of the department's daily operations. You flag 2 items for the incoming shift: the loaner set awaiting the missing trial sizer from the company representative, and a washer disinfector spray arm nozzle that you found slightly more occluded than usual during your cleaning inspection, suggesting that mineral scale may be building and that a descaling cycle should be scheduled. These are not crises. They are notes. The next shift will handle them. You prepare the communication for the outgoing handoff. You wait for the next shift's technician to arrive. The incoming technician arrives for the evening shift. You conduct the handoff. You review the shift record together. You communicate the status of the loaner set and the spray arm observation. You indicate which instrument trays have been sterilized and are stored and ready, which trays are still in process at various stages, and the instrument tracking system status for each. You communicate any outstanding requests from the operating rooms for the evening's cases. The incoming technician has the information they need. They acknowledge it. They are ready to begin. You remove your clean area scrubs. These go into the facility laundry. You change into your street clothes. You collect your personal belongings. You badge out through the department entrance. The department door closes behind you. Behind that door, the cycle continues. The instruments that are somewhere in the middle of processing will be completed by the evening shift. New contaminated trays will arrive as afternoon surgical cases complete. The washer disinfector will run additional cycles. The sterilizer will run additional loads. The biological indicators will be incubated and read. The storage shelves will receive new packages. The operating rooms will draw from the shelves as tomorrow's cases are set up. The cycle turns and does not stop. You had no direct contact with any patient today. No patient saw you, spoke with you, or was aware of your existence during their surgical procedure. The instruments you cleaned, inspected, assembled, packaged, sterilized, and delivered were the only evidence that you were there. Those instruments will be opened on the surgical field, used for their intended purposes, and returned to you after the procedure. You will process them again. This is your job. It is quiet. It is essential. It happens in a basement, under fluorescent lights, in the middle of the night as often as during the day, by people whose certifications contain more syllables than most people's job titles, and whose work is invisible to everyone who benefits from it. The instruments are clean. You made them that way. You have completed a shift in the sterile processing department. During this shift, you cleaned, inspected, assembled, packaged, and sterilized multiple instrument sets containing several hundred individual instruments. You ran biological indicator tests confirming the efficacy of your sterilization processes. You identified and quarantined a defective instrument. You identified and reprocessed an inadequately cleaned lumen. You received and inventoried a loaner instrument set. You delivered priority items to the operating room suite. You completed all required documentation. You cleaned the equipment. You did all of this in a basement. You are, in all practical senses, the last line of defense between a contaminated surgical instrument and a patient. This is not a small thing to be. It is also, for large portions of your shift, a very quiet thing to be. The two are not in conflict. Quiet and important coexist in many places. This is one of them. If you would like to do this again, there is another shift tomorrow. The instruments will be waiting. They are always waiting. They are very patient in the way that inanimate objects have no choice but to be, which is absolutely. Thank you for watching. Good night, or good morning, or good afternoon. Whatever it is where you are, sleep well.